Okay, so we are going to be discussing trig functions today. There are 6 trig ratios that you need to be familiar with. Back when I used to teach 8th graders and 9th graders algebra, and we would talk about trig, had this little skit that I had written where they learned how to keep straight all of those trig ratios. Since you guys are college students, you'd probably be bored silly if I tried to explain it to you. But there's a lot of little acronyms that will help you out. The one that I grew up with and the one that I made this little skit about is, let's do this. Let me get this set up so it will mark hopefully correctly. Okay, hang on. All right. Have you ever heard of SOHCAHTOA? Okay. So let me explain to you how this might help you learn something about these trig ratios. First of all, where they come from would be the ratios of sides in a right triangle. Okay, so these trig ratios work with right triangles. And if you think about the sides in a right triangle, let me just sketch one over here for you so you can kind of look. Here's your right angle. Then the angle that we're going to be interested in when we're working with the trig ratio will not be the right angle, but it would have to be one of the acute angles. So let's say this angle right here is the one that I am interested in. I have 3 sides in a triangle. The one that will never change and is always the same is which one? Well, that's the angle. What about sides? What's the longest side in a right triangle called? Hypotenuse. This is going to be your hypotenuse. It's always the side that is directly across from your right angle. Now, that leaves 2 legs in my right triangle. So in order to be able to differentiate between the 2, here's how we label them. If I have to go through the triangle to get to one of the legs, we're going to say that is the opposite leg. Okay? It's opposite this angle. The one that is right next to it is called adjacent. Because if you're adjacent to something, you're next to something. So that's where the O and the A and the H are coming from when we talk about SOHCAHTOA. Okay? So, that's going to help us get these ratios down. Because what we're looking at, if we're talking about, say, this sine, and technically it's S-I-N-E, but we use 3-letter abbreviations, so it looks like sin. By the way, this right here is the Greek letter theta, which is typically used to represent an angle when we're talking in particular about things with trig. So when we say we want the sine of angle theta, if I'm looking at this, sine is going to be opposite over hypotenuse. S-I-N-E is opposite over hypotenuse. Now, the way they defined it here, and this is another way you can do it, is they expressed it in terms of the x side. Typically, when you think about these angles, let me see if I can draw. Now, let's do this. We can put it right here. Okay, let's say I have a coordinate plane. Okay. And if I put a central angle, it means that the angle is coming from the origin, all right? Then what I have would be a side of the triangle that's on the x-axis. So it's my horizontal length would be an x length. My vertical length would be a y length. And if you were to picture this in terms of this angle being inside of a circle, you could think of this as your radius. And they would call that your R value. So when we talk about opposite over hypotenuse, that would be the same thing as y over r. Okay? And it doesn't matter to me which way you learn these. You just have to know how to put the ratio together correctly for the different trig functions. Okay? So a sine ratio is opposite over hypotenuse. That's the SOH part of SOHCAHTOA. We have three primary trig ratios. Sine is the first one we talk about. Guess what the next one is? Cosine. If you've ever paid attention on a calculator that is equipped, a scientific calculator is equipped to do trig ratios, there's only three, even though there are 6 trig ratios, there's only 3 buttons on there. Sine, cosine, and then we'll talk about the other one in a minute. Now, cosine is a different ratio, clearly, has to be. And if you were to tell me, based on what you see here, what you think it would be what? That is correct. Adjacent over hypotenuse. Or x, because that's going to be the horizontal side, over r. Okay? What do you think is the third most important? Tangent. You are exactly right. If you're looking on your calculator, those are going to be the 3 keys you have. And your tangent ratio is what? Opposite over adjacent. Exactly. It doesn't use the hypotenuse at all. Okay? So those are, if you can remember, SOHCAHTOA. In fact, I'll give you one more way you might remember it. If you were growing up in the 70s, you might have had somebody teach it to you this way. Some old hippie came around here tripping on acid. I know, that's pretty awful, isn't it? I've never used that to teach it, but I will let you know there are some people, that's how they remember it. So, whatever works for you, you just got to make sure you get these ratios down. So we've got half of them that we've covered now. Sine, cosine, tangent. You need to memorize those, all right? For our first test, I'm going to expect you to have those memorized. And I realize right now we're kind of talking in terms of definitions. Everything's very abstract. When we start using it, you'll see a little bit better how to put this together. Now, there are 3 more we haven't yet talked about. And that is going to mean that if I were to take the reciprocal of each of these ratios, I get a new ratio, right? Okay, because opposite over hypotenuse is going to be a different fraction from hypotenuse over opposite. So what that means is we have a set of ratios that are reciprocals of these. And if I can keep them paired up, it makes it really easy to see how to come up with those. Here's the way that I do it. My S for sine is going to pair with the C for my reciprocal. Now, it can't be cosine because that's one of my 3 primary ones. So what's the other ratio that starts with a C, but it's not cosine? Exactly. Sine and cosecant are reciprocals. All I have to do is flip the ratio, and I've got that relationship. Just like the S and the C were paired up for sine and cosecant, I'm going to keep pairing up the S and the C. When I move to cosine, it's going to pair up with what is the reciprocal? Secant. You're exactly right. And that leaves the reciprocal of tangent to be cotangent. Those are the only ones that the co-function is the reciprocal of the original. Okay? Does that make sense? All right, so these are just some organizational tools to kind of help you see if you can get that general information in place. Now, we talked a little bit about terminal sides. I believe, of an angle versus initial side. Because we said if we were drawing an angle, let me just kind of put this back up here again in case you've forgotten. So let's say we have a coordinate plane. And typically, if I were to put something up here, and this is my angle, because we said if it's in standard position, we're always moving counterclockwise, right? Okay, so the x-axis, the positive side of the x-axis was our initial side. That means where the angle ends, where I'm drawing, the other part of the angle is my terminal side. Y'all remember talking about that, right? Okay, so it passes through the point 12,5. Now, I have just kind of stuck this thing up here. I haven't put a scale on it. This is not going to be to scale, so bear with me. But let's just put a point on here, and let's say this point right here is the ordered pair 12, 5. Okay? We would want to find the 6 values for angle Q, the 6 trig values. Now, first of all, if I'm going to come up with those trig ratios, I have to have what kind of shape? A right triangle. So the only way I'm going to get a right triangle out of this is when I drop a perpendicular to the x-axis. Anytime I have an angle, if I'm going to be working with trig ratios, I never draw a horizontal line. I'll never go to the y-axis. I'll always draw a line that drops to the x-axis. Okay? Which means it's going to form a right angle, and that gives me that right triangle. Now, again, I did not draw this to scale. I apologize for that. But let's see if you can help me label what I should know about these sides. So if this is the ordered pair 12, 5, should I know how long each of the legs are? Okay, think about it. I had to go 12, which direction? What comes first in an ordered pair? Yeah, it's the x value first, y value second. Oh my goodness. I already know I can express these trig ratios with x's and y's and r's, right? So if this is going through the point 12, 5, would you agree that this distance along the x-axis is 12? You had to go 12 to the right, and then how many up? 5. What if there had been a negative in front of the 5? Then instead of this point being in the first quadrant, it would have been in which quadrant? The fourth. Very good. And I would draw it that way, and I would still put 5 on that y value, because remember, if we're talking about a distance is going to always be a positive value. I know in terms of position, it puts it in the fourth quadrant. But in terms of calculating what I would need on my triangle, I would still put a positive 5. Now, I only have 2 sides labeled. Is there some way to get the third side? And then do what? Excellent. All right, you are telling me how to use the Pythagorean theorem. So a squared plus b squared equals c squared is Pythagorean theorem, which works only with what kind of figure? Right triangle. So that's why it's going to help us out here. Since we've constructed this right triangle, that will allow us to figure out how long this hypotenuse is. So if I took 5 and I square that, add 12 and I square that, that's going to be my hypotenuse squared. Remember in Pythagorean theorem, c is always the length of the hypotenuse. All right, 5 squared is 25. How much is 12 squared? 144. That's equal to c squared. So if I add those together, I get 169. And to find c, I would need to do what? Take the square root. Excellent. And because it's a length, I'm always going to use the positive value. The hypotenuse will always be a positive number. How long is my hypotenuse? 13. Okay, now that I got a triangle and I've labeled all the sides, let's see if you can tell me what would be our 6 trig functions. So we're going to start off, remember we're using angle Q. So the sine of angle Q would be what ratio? If I'm looking at my triangle, sine is what over what? Opposite over hypotenuse. So that's going to be what fraction? 5 over 13, because the hypotenuse is 13. Good. All right, let's get the cosine. Cosine of angle Q is, what's that ratio we're supposed to remember for cosine? Adjacent over hypotenuse, so that's going to be what fraction? Good, 12 over 13, because the adjacent side to angle Q is the leg. It'll either be horizontal or vertical that's right next to where the angle is. So in this case, it's the side that's 12 over the hypotenuse is 13. Let's get the tangent of angle Q. So the tangent of angle Q is, what's that ratio? Opposite over adjacent. What's going to be that fraction?
5 over 12.
Excellent. Here is angle Q right here. Okay. So opposite, if I go through the triangle, that gets me to 5. Over adjacent is 12. Now, I hit my 3 main trig ratios. Can we do the reciprocals?
Yes.
All right, let's see if you can tell me. The reciprocal of sine is which one? Cosecant. Very good. So the cosecant of angle Q would be what ratio? 13 over 5. Excellent. You guys are either really quick learners or you already knew some of this. What is the reciprocal of cosine? Secant. And the secant of angle Q is 13 over 12. Very good. And then the reciprocal of tangent is? And the cotangent of angle Q would be? Perfect. Okay, make sense? All right, let's go to page of notes.
So that would be.
That's it. We just had to find the 6 ratios. Okay. Now, this one's a little bit different because it says find the 6 trig functions of the angle Q in standard position if the terminal side of Q is defined by 3x minus 2y equals 0, where x is less than or equal to 0. Okay, don't let that confuse you. We're just going to have to pull in a little more algebra to get this thing done. So I know there's a terminal side, and it's going to have to be wherever this line, 3x minus 2y equals 0, is graphed. So should we start with a coordinate plane? I think so, because this may or may not be in the first quadrant. Goodness, okay. All right, so there's my y-axis, here's my x-axis, and I'm going to have to figure out where 3x minus 2y equals 0 needs to be. So ideas on how to come up with where this thing should be graphed. All right, let me give you a couple of options. If I wanted to put it in slope-intercept form, tell me what that is. Well, that's the slope. Slope-intercept form of an equation is y equals mx plus b. Good. Okay, if I wanted to put it in slope-intercept form, I could do that, and then I could plot the y-intercept, and I could use the slope to get another point, and I could go from there. All right, here's another option. Could I build a table, pick some values, say plug something in for x, see what I get back for y, and how many points does it take to graph a line? It takes 2 to get a line, but the smart thing is to get a third point to make sure they all line up. Because if I messed up on one of them, I'm going to get a line, but it might not be the right one. If all 3 line up together, that tells me I probably did it right. Now, if I were to ask you what you're more comfortable with, how many of you say, I'd rather use slope-intercept form? How many of you say I'd rather make a table? Okay, I see a few more hands for that, so let's do that. what I would consider doing is if we've got 3x minus 2y equals 0, how about if I get the x on one side, the y on the other? I think that might make it a little easier on the plugging in. So could I add 2y to both sides? And if I do that, I get 3x equals 2y. Okay, now, keep in mind, we had a domain restriction up here. We want our x values to be less than or equal to 0. So really, if I'm building a table, I'm going to pick something for x, I'm going to plug in, and I'm going to see what comes back out for y, okay? And then I'll have some ordered pairs. Now, what's going to be the easiest thing to put in for x? 0. Because if I put in 0 for x, 3 times 0 is 0. And if 0 equals 2y, what is y? 0. All right, this thing is passing through the origin. So I know that's a point that's on the graph. Now, we need to pick some number that would be negative because x is supposed to be less than or equal to 0. And here's where you want to be smart. I could pick -1, but if I pick -1, what kind of number am I going to get for y? I think I'm going to get a fraction, won't I? Because 3 times -1 is -3. And if -3 is equal to 2 times y, that's going to give me a fraction. So let me give you a suggestion. If you have coefficients in front of both the x and the y when you're trying to come up with some points for your table, think of numbers that would be that would have both 3 and 2 as a factor, okay? Because if I do that, then I should be able to come up with something that is going to work. So if I think about 3 and 2, I could definitely use something like 6. Now that's on the positive end. If I go to the negative end, then I'm looking at putting in, say, a negative, well, let's do it this way. Yeah, I want it to multiply together to give me 6. So if I let x be a -2, because my x value is supposed to be negative, here's what I would have. -6 equals 2 times y. So y would have to be what? If I divide both sides by 2, what does that make y? So y would equal -3. Now, here's what I have. If I were to mark off some units here, when x was -2, we said y was -3. Okay, that's going to be a point that's on here. Let's just double check and pick something else. So we knew 6 was something if we multiplied and got both sides to be 6, that should work. What would be the next number both 3 and 2 would go into evenly? 3 won't go into 8. How about 12? Yeah. So 3 times what would give me a -12? -4. So if I used a -4 for x, then that would mean that 3 times -4 is -12. And if -12 is equal to 2 times y, what would that make y? A -6. So again, if I wanted to double check this, I could go to a -4 for the x, down to a -6 for the y, and yes, these do line up. Okay? I could pick other points, but those would be the easiest ones. Because if I pick any of those other numbers that were in between, I'm going to get fraction values back for y, and that's going to be a little harder to graph. So here is where this line needs to be drawn. Now, what quadrant am I in? I'm in the third quadrant. And since it's in standard position, doesn't that mean that this angle has to be started at the positive value of the x-axis and it goes all the way around here? Yeah, okay. Now, this is the part that looks a little goofy because if it's not in the first quadrant, or in the fourth quadrant, then I'm not going to be using this initial side of the angle as part of my right triangle, right? Okay, this is not going to be part of the right triangle because this is the side that my angle ends on. Remember I said you're always going to draw a perpendicular line back to which axis? The x. It doesn't necessarily have to be on the positive part of the x-axis. This one is going to be on the negative part. So what I'm going to do is make my right triangle here. And when I find these ratios, okay, remember that we're going to be in the third quadrant. So we will pay attention to signs, S-I-G-N-S, to see whether our x values and our y values should be negative because of where we're located. So you can have negative trig ratios, all right? But your hypotenuse will always be what sign? Positive. Okay, so let's make sure that part makes sense. I am not coming up with the measure for angle Q. I mean, I know angle Q has to be more than 180 degrees, right? Because I started here and I went all the way around over here. But when I draw this to get the ratios that are going to go with this angle, it's going to be based off of this triangle. All right, so having said that, let's see if you guys can tell me what would be, and I could draw it here, I could also draw it here. All right, the difference is I'm going to get fractions that reduce down if I use the -4, -6. If I were to use the triangle here, I mean, that's still got the same angle, doesn't it? These are called similar triangles because they both have the right angle. And this is the same angle in the smaller triangle as it is in the larger triangle, okay? So what I'm saying is this angle right here is in this smaller triangle, but it's also in the larger triangle, and these two are going to be the same. So my triangles are similar. It means if I use the smaller triangle, I won't have to reduce the ratios. If you want to use the larger triangle, double check it and see if you come up with the same ratios. Now, looking at the smaller one, tell me how we would label this side right here. Let me do this. This side right here. How would we label that side? Yeah, and because we're on the negative part of the x-axis, let's put -2. This is going to help us on getting our signs correct in a minute. I know I said distance is always a positive value. But when we're talking about the trig ratios, we do want to pay attention. This is going to indicate where we are in terms of the 4 quadrants. So our x value is -2. What was our y value that goes with that? -3. And we need to find that hypotenuse length. So how are we going to do that? Pythagorean theorem. So if we do a squared plus b squared equals c squared, oops. We're going to have -2 in parentheses squared. That parentheses is important because if you go to your calculator and you don't put -2 in parentheses and you just hit squared, it's going to give you back a -4. And that's not right. I'm squaring -2, so that means -2 times -2, which is a +4. Plus, we got to square -3. And this one is not going to be something that's a perfect square. It means we're going to get a radical for the length of the hypotenuse, because what happens when you square -2? You get, and 4 plus 9 is only 13. So if I take the square root of 13, that's irrational, right? If I put it in the calculator, I get a nasty looking decimal. We want to keep things exact. So we're going to put the square root of 13 as that hypotenuse length. So far, you with me? All right. Now we're supposed to give what the 6 trig ratios would be. So let's see if we can do that. The sine of angle Q is going to be what? If I'm looking at my triangle, sine is opposite over hypotenuse. So tell me what to write down. Negative 3 over square root of 13. Negative 3 over square root of 13. Good. Okay, let's get the cosine. And that's going to be what? Adjacent over hypotenuse, so that would make it
-2 over square root.
good. Negative 2 over the square root of 13. Tangent is opposite over adjacent, and that gives us,
2 over -3.
all right, the opposite would be what now?
-3.
There you go. A negative 3 over a negative 2. Now, what does a negative divided by a negative give you? Yes, that is a positive 3 over 2, so you want to clean that up. If we'd used the larger triangle, would you agree that would have been a negative 6 over a negative 4? And does that reduce down to 3 over 2? Yes. So there are many different ways you could construct the triangle. I would say use the smallest pair you have that has integer values so you don't have to reduce. And then we can get those reciprocals real easily, right? What's the reciprocal of sine?
Square root of 13 over negative.
And what ratio is that? The reciprocal of sine is, remember pair up S and C? Cosecant, good. So cosecant of Q would be, and it doesn't matter if you put the negative with your numerator, with your denominator, or just in front of the whole fraction. As long as there's only one negative sign, that means the same thing. All right, what's the reciprocal of cosine? And the secant of angle Q is? Very good. We're going to have square root of 13 over negative 2, or you could put the negative sign on top or out in front, doesn't matter. What would be your cotangent? 2/3. Excellent. All right. Any questions so far, guys? All right, good. Now, we're going to find the 6 trig functions for what are called quadrantal angles. We have a lot of names that sort of sound made up sometimes in trig, but guess what quadrantal indicates? They're what? They're actually going to be on the axis, okay? So in other words, think about what it would look like if you drew an angle that's 90 degrees, okay? You would have your, oops, let me get this where I can write. Okay, you would have your coordinate plane, and if we were doing a 90-degree angle, that would mean that we would start here at the x-axis and then we would come up to the y-axis. That's 90 degrees, right? Okay, what would be another quadrantal angle? How many degrees? 180. Or
240.
actually 270. And if you made a complete circle, that's how many degrees? 360. All right, so we're going to look at special values for these angles that end up being on an axis, and they're called the quadrantal angles. Now, let me first try to explain this the way I learned it, and then I'm going to give you something that I just learned a couple of years ago. I also teach calculus, dual credit calculus in Maybank. And it's so cool. The teacher that I teach with there, she was my teacher in high school. Believe it or not, she's still alive and kicking and really. Yes, I'm talking about Miss Hyde. Yes, I love Miss Hyde. And she had a student a couple of years ago who came in. Did she teach you about hala and ahala? There you go. So we're going to learn that because that's going to help too. But I want to explain a little bit about what this actually means. So here's what I want you to picture, okay? Let's say we were going to figure out what would be the sine of 0 degrees. Now, first of all, logically speaking, if my angle inside that triangle is 0 degrees, do I have a triangle? No. So here's what I want you to kind of visualize. Let's say we had this angle that's pretty small, and we want to picture what happens if this thing starts closing up and it gets closer and closer and closer until it just finally is on top of itself on the x-axis. Now, here's what I want you to think about. Okay? If this thing starts closing up, and let's just say this is a unit of 1 right here. All right, so we're talking about moving out on the x-axis 1 unit. And this part of the triangle is going to start squeezing down toward the x-axis. As it gets closer and closer to the x-axis, what's the length of that getting closer and closer to? 0. You're exactly right. So this is kind of a hypothetical. We're picturing if this were to happen, that distance is going to be 0. It's going to get really, really close to it. Now, if the hypotenuse is coming down on top of it, how long would the hypotenuse be when it lands on top of the x-axis? It would also be 1. Now, we know that's not really a triangle, but that gives us the ability to figure out what these would be. So here's what I want you to consider. Well, since they've been using angle Q, we'll just stick with that. And let's say if this were the triangle we were looking at, and I had asked you to find the sine of 0 degrees. Okay, sine, we said, is what over what? Opposite over hypotenuse. If I look at this triangle where the adjacent is 1, the opposite is 0, and the hypotenuse is 1, what would that make my ratio? Opposite would be how long? 0 over what would be hypotenuse. And what is any fraction where 0 is on top and the denominator is not 0? 0. 0 divided by anything is 0. Okay? So the sine of 0 degrees is 0. Now, what about the cosine? Cosine's not opposite over hypotenuse, it's what? Adjacent over hypotenuse. Look at this diagram. What would that be? 1 over 1. And any number divided by itself is 1. Okay? Think about tangent. Tangent is what? Opposite over adjacent, which is also 0 over 1, which is 0. Okay? Now, can we get those reciprocals? Sure can. That would mean that the cosecant of 0 is how much? Well, I'm supposed to do what with my fraction? Flip it. And when I flip it, I get what on top? Over 0. Now, what happens if I have 0 in the denominator? It is undefined. It does not exist. So that means this is undefined. Okay? What about the reciprocal of cosine? It is secant. Good. Got to keep those C's and S's paired up. So the secant of 0 is, when I flip 1 over 1, I just get 1. Okay. And what's the reciprocal of tangent? Cotangent. And the cotangent of 0 would be what? 1 over 0, which is undefined. Very good. Okay, now, here's what I want you to get. If I'm looking at a quadrantal angle, these are pretty much my options. It's either going to be 0, it's going to be 1, or it's going to be undefined. It doesn't exist. And I could actually construct these, kind of visually picture, if I get super close to that axis, and remember, I'm always dropping a perpendicular back down to the x-axis, so I can kind of visualize what happens as I squeeze, then I'm going to see these. The only additional value that can show up on a quadrantal angle would be if instead of working over here, what if we were looking at something like 180? What's going to be the new value that might come up? -1. Okay, 0 doesn't have a sign, so 0 is just 0, undefined is just undefined. But I could get a negative one if I'm working over in one of those other quadrants. Now, we can do that each time, and we can kind of visualize it, calculate what those would be. But I'd mentioned this little shortcut to help you learn. You can do this, although it occurred to me yesterday, we were doing this in calculus yesterday, and I thought, please don't kind of chant this as you walk through the airport. You'd probably get in trouble. They might think you were a terrorist or something. But here's what you could learn. Let's say we have for sine, and I'm going to go ahead and use a little space down here, even though this is a different question. So for the sine ratio, what I know is that it starts with a value of 0, okay? So at 0 degrees, 90 degrees, 180, 270, and then back to 360, that's going to give me one full revolution. And I should be able to figure out all these quadrantal angles if I know that the sine of 0 starts with a value of 0, and then all I have to do is realize that is an axis angle, okay, because it's on the x-axis. And if it's on the x-axis, it's going to have a value of 0. Now, if it starts with the A, here's what you learn. It is a hala. A-H-A-L-A. For sine ratio, it's a hala. That means you start on the axis, which means you've got a value of 0. Then it goes to a high. What was the highest value we got? You remember, we looked at these as we went through sine of 0 degrees. What's the highest value you're going to get on a quadrantal for sine or cosine? The biggest number we saw up here was 1. Then you're back to an A. If you're on the axis, the value is 0. Now, what do you think would be the low value? Nope. Actually, it's going to go down to -1. And then we go back to the axis for 0. Okay? If you don't know what the sine graph looks like, it does this. We call it a sinusoidal curve. It's a cycle. It just goes up and down and up and down. There's a lot of things, like think about radio waves or television waves. There's a lot of things that occur in the real world that do this, okay? And that means you'll never have a sine ratio that's higher than 1. You'll never have a sine ratio lower than -1. Where we got these undefines, that occurred not on sine or cosine, but it was on cosecant and cotangent, okay? So your sine and your cosine will always be a value between 1 and -1. And if you can learn a hala for those quadrantal angles, rather than having to draw them and visualize, it gives you a quick way to figure out whether it's 0, 1, or -1. Does that sort of make sense? All right. Guess what you can do with cosine? Same thing, except notice where we started for cosine of 0 degrees. It wasn't 0, it was what value?
1.
And 1 would be what letter? A, H, or L? H. It's a high point. So it's going to start with the H, and that means we have H-A-L-A-H, hala. Okay? Cosine starts high, so it's hala. Sine starts on the axis, so it's a hala. And that means I could go through at 0 degrees, the cosine would be 1. At 90 degrees, what would the cosine be? 0. What would the cosine be at 180? -1. 270 is?
0.
And then 360 is high, so it's 1. Okay? that would be a quick way to sketch this out. Now, here's the other thing that's kind of cool. We're going to learn about some other relationships between these ratios. And one of them, I'm just going to kind of give you a heads up because I don't know if you've recognized this, but have you ever had the experience in a math class where maybe the first time you hear something you go, huh? And then you think about it for a little bit, you come back, and then when you hear it the next time you go, oh. I mean, I know that's the kind of the way I learned. So that's sort of what, we've got a lot of information we're covering here. So we're going to kind of learn it in layers. I'm going to throw some things out, pre-teach a little bit here and there so that when you hear it again, you might pick up on something you didn't necessarily pick up on the first time. And again, like I said, I'm going to try to get these videos out there so if you decide I need to listen to it again, you can. But here's a relationship that's going to be kind of helpful in terms of these other quadrantal angles. I'm not going to have to memorize anything except hala and hala for sine and for cosine, because guess how you could express tangent? Actually, look at this. Let's say we were to take sine over cosine. All right, now you tell me, sine is what over what? Opposite over hypotenuse, okay? And if we were to divide that by cosine, what's cosine? Adjacent over hypotenuse. Okay, we got a fraction divided by a fraction, which kind of looks like a mess if you leave it in this form, but can't I divide fractions this way? Opposite over hypotenuse divided by adjacent over hypotenuse. I could write it horizontally. And if I'm dividing a fraction by a fraction, how do I clean that up? Have you ever heard of leave, change, flip? You leave the first fraction just like it is, so we're going to have opposite over hypotenuse. We're going to change that division to multiplying. And then we're going to flip the second fraction. So the hypotenuse on bottom will become the hypotenuse on top. Over, we'll put the adjacent on bottom. And what can I do with those two hypotenuse? They cancel, because if I'm multiplying fractions and I have a common factor on top and bottom, they cancel. What ratio does that leave me with?
Opposite over adjacent.
Do you know what ratio opposite over adjacent is? Oh my gosh. So if I know sine and cosine, guess what? I could be able to figure out the tangent of one of those quadrantal angles if I simply do sine divided by cosine. Could I get the cotangent? Guess what I'd have to do instead? Put the cosine on top, because that would flip this and it would make adjacent on top, opposite on bottom. Could I get the secant? Because the secant is just the what? Reciprocal of cosine. And I could get, so as long as I know cosine and sine, I can actually get all of them. All right? So that's going to be hopefully a little tool that will help us on these quadrantal angles. If we were to look at this question, angle Q in standard position with a terminal side passing through 0, -5. Let me go back up here to this coordinate plane that we drew earlier. Which axis would 0, -5 be on? Would it be on the positive or negative end of either the x or the y? Where's 0, -5? The negative of y. You're exactly right. 0, -5 is going to be down here. Okay? Which means that's how many degrees? 270. So I could come over here to where we wrote out a hala, and I could look in my 270 column, and I could come up with all 6 from there if I wanted, right? Does that make sense? Let's do it verbally. I don't really have room to write down, but we could do this. So let's say we're looking for the sine of 270. What would that be? The sine of 270, I'm hearing some people say -1. Y'all agree?
Yeah.
That's it. What would be the cosine of 270? 0. Excellent. Okay, let's see if you could tell me the tangent. The tangent needs to be, which one goes on top, the sine or the cosine, if I'm finding the tangent? The sine would go on top. So that would mean -1 divided by 0, which is undefined. The tangent at 270 is undefined. All right, now let's try some reciprocals, okay? What would the cosecant of 270 be? What do you do to get cosecant? You take the reciprocal of sine. And since the sine of 270 is -1, what happens if you flip -1? It's still -1, isn't it? -1 over 1. Remember, if it doesn't look like a fraction, you can always make it a fraction by putting it over 1. So -1 over 1, when I flip it, is still going to be a -1. All right. Talk to me about the secant. Secant is the reciprocal of cosine. So if I'm looking at cosine of 270, that's 0. So think of it as 0 over 1. What happens when you flip it? It becomes 1 over 0, which is undefined. So your secant at 270 would be undefined. And we could do the same thing to find the cotangent. You could put cosine over sine, or you could take the reciprocal of tangent if you've already found it. So if I do cosine over sine, 0 over -1 is 0. Make sense? Okay. So let's look at this. Conditions for undefined function values. We want to identify the terminal side of a quadrantal angle. If it tells you it's in standard position, your initial side is where? The positive end of the x-axis. That's almost always going to be the case. And your terminal side is wherever the other part of your angle ends up. So if the terminal side of the quadrantal angle lies along the y-axis, then tangent and secant will be undefined. Okay? So if the terminal side is either 90 or if it's 270, then tangent and secant will be the ones that are undefined. So if that helps you to kind of tuck this away, you can do that. If instead you want to use a holla and figure it out, you can as well. If your terminal side lies along the x-axis, so if it's 0, 180, or 360, then cotangent and cosecant are going to be the ones that are undefined. Okay? And then there's this little table here. So let's see if we can remember how to fill this in. For sine, is it holla or a holla? Where do we start on sine? Good, with the A. So if we're starting with a holla, that means we start with what value?
0.
Axis is 0. What would 90 be? 1. What would 180 be? We're back at A. A is
0.
good. What's 270? -1, because that's a low point. And then 360 would be 0, because we're back at an axis. Very good. Okay. Cosine, we have to remember what? Holla. Start with the H. So that means we start at a high point. What would that mean that the cosine of 0 is? 1. 90 is 0, because we're back at an axis. What would 180 be? -1, because that's a low point. Then 270 is 0 and 360 is 1, because we're back at a high point. Now, just like I told you a minute ago, let's see if we can get the ratio for tangent by taking sine over cosine. So 0 over 1 is 0. Very good. They've already told us that the tangent of 90, because tangent at 90 is on the y-axis, that's going to be undefined. What would the tangent of 180 be? 0. 0 over negative 1 is 0. What would the tangent of 360 be? 0. Look at that. All of these are, for the tangent on the quadrant angles, are either 0 or undefined. Okay? Now, cotangent, the same is going to be true, but it's going to be flip-flopped, because cotangent is undefined anytime you're on the x-axis. So it starts off undefined. What does that mean we get for the cotangent of 90? Remember, cotangent would be cosine over sine. 0. Undefined, negative 1 over 0 is undefined. What about the cotangent of 270? 0. Very good. Okay, secant is the reciprocal of which one? Of cosine. So if I look at my cosine column and I take my reciprocal, what is going to be the secant of 0? It's got to be the reciprocal of cosine. If cosine is 1, what do you get when you flip 1? You still have 1. 1 over 1 is still 1 over 1 when it's flipped. If I think of 0 as 0 over 1, when I flip it, that's undefined. What's going to be the secant of 180? It'll still be negative 1, because negative 1 over 1, when I flip it, still gives me a negative 1. And what would that make the secant of 360? If that's going to be 1. Very good. And then let's fill in cosecant. We already know that because cosecant is the reciprocal of which one? Sine. The reciprocal of 0 is undefined. What's going to be the reciprocal of 1? 1. Reciprocal of 0 is undefined. The reciprocal of negative 1 is negative 1. And we've got our table all filled in. Okay? That means we're going to be able to move through some of these things a little faster. Here are those reciprocal identities that I've already told you about. So you've got that information there. Again, this is something you need to memorize. Let's see if you can figure out what would be the tangent of angle Q if they tell you the cotangent of angle Q is 4. Say that again? Exactly, because cotangent doesn't look like a fraction, but could I make it look like a fraction? If I do what? There you go. Write it as 4 over 1. So the reciprocal of cotangent is tangent. That means when I flip my fraction, I get 1 over 4. That's pretty easy, isn't it? Yes? Okay. Let's go to the next page. And we're going to start with secant when we're given the cosecant. And this one has a radical in it, so let's make sure that doesn't give us any trouble. Is secant the reciprocal of cosine? Yes, it is. So to find the secant, I would probably need to do what? I'd need the cosine. They gave it to me. So what am I going to do with the cosine? Flip it. If I flip this, does the sign change? No. Keep the same sign, okay? We're not going to, that would be a negative reciprocal if we're changing the sign. We just want the reciprocal. So it's still going to be negative. But now what's on top? Square root of 20 over 2. Now, real quickly, I just want to review you on this, and then we'll probably stop here today. That radical is not simplified. Do you guys remember simplifying radicals? Okay, it's not a perfect square, is it? If I put square root of 20 in my calculator, I get back a decimal. But I can simplify it. Do you remember how? How do you simplify radicals? Yeah, you've got a couple of different methods. You can factor. I always prefer to use prime factorization. That means I'm going to figure out what prime numbers would multiply together to give me this. You may have had an instructor who said, well, you need to memorize all your perfect squares. And then if your perfect square is a factor of this, that'll be the way you want to factor it. And if you know those perfect squares, that's fine. I just find for most people, especially if the number gets very big, you may not recognize that 64 is a factor of some big number, and you would not be able to figure out how to factor it. So let me just show you a method. If I were to take 20 and I wanted to write it in prime factors, I like to write it down this way. Instead of a factor tree, I do it kind of like an upside down division. And first of all, remind us, what are prime numbers? What's the definition of a prime number? It's divisible only by itself and 1. There you go. If any other number divides into it other than itself and 1, it's not prime. It's composite. So what's the smallest prime number? 2. Think about it for a minute. Most people say 1, but 1 doesn't actually meet the definition of a prime number. If it's got to be divisible by itself and 1, that's the same number. So the smallest prime number is 2, and it's the only prime number that's even. So 2, what would be the next one? 3, then 5, then oh, be careful. Can I use 9? Because 3 goes into 9. That one's not prime. 11 would be the next one. We keep going. All right, so here's the deal. As long as it's an even number, divide by 2 as long as it stays even. And 20 is an even number. 2 goes into 20 how many times? Is that still even? So 2 goes into 10 how many times? That is not even, and is that a prime number? When I get a prime number on bottom, that's when I know I've got this thing factored. 20 is 2 times 2 times 5. Now, because it's a square root, that means I want to know what can you multiply times itself to get that. In other words, I'm looking for pairs. Do you see a pair of factors that match? I have a pair of 2s. Anytime I find a pair when I have factored this using prime numbers, that means that one out of that group that I circle can come outside the radical. 2 times 2 is 4, and the square root of 4 is 2. So this could simplify as negative. I'd have a 2 on the outside, because that's what I had a pair of. What would stay underneath the square root sign? 5. And then I have a 2 in the denominator. Now, by simplifying this, what does that let me do? Exactly. I have a 2 on top, 2 on bottom. That can reduce down. The simplified answer for the secant of angle Q would be negative square root of 5. Okay? So we may practice a little of that as we go along too.